Welcome to AI Frontiers, where cutting-edge artificial intelligence research meets practical innovation. Today we explore 16 groundbreaking computer vision papers from October 31st, 2025, revealing revolutionary advances that are transforming how machines see and understand our world. Picture this scenario. You're sitting in a doctor's office, and instead of cold electrodes being attached to your chest for an electrocardiogram, a small radar device across the room silently monitors your heartbeat through the air. No wires, no discomfort, just invisible waves reading the rhythm of your heart with stunning accuracy. This isn't science fiction anymore. It's happening right now in computer vision laboratories around the world. Researchers have developed systems that can monitor vital signs completely contactlessly, using radar technology that penetrates through clothing and captures the subtle movements of your chest as your heart beats. The implications are staggering. Continuous health monitoring without any physical contact, perfect for patients with burns, infectious diseases, or those requiring long-term observation. This breakthrough represents just one example of how computer vision is revolutionizing healthcare, making the impossible suddenly possible through the marriage of electromagnetic waves and artificial intelligence. These 16 papers represent far more than academic exercises. They're glimpses into a future where machines don't just see, but truly understand our visual world. From revolutionary medical monitoring systems that work without touching patients, to artificial intelligence that can detect deepfakes with unprecedented accuracy, to underwater robots that navigate murky depths with superhuman perception. The research spans an incredible range of applications. Generative models that can create Hollywood-quality visual effects on smartphones, security systems that can trace synthetic images back to their creators, and spatial reasoning systems that help AI understand the three-dimensional relationships between objects. Each breakthrough builds upon decades of foundational research while pushing the boundaries of what's possible. Today's episode will take you on a journey through these latest advances that are reshaping how artificial intelligence perceives, processes, and responds to visual information, revealing solutions to problems you didn't even know existed. Computer vision stands as one of the most transformative areas of artificial intelligence research, and understanding it requires thinking about it like teaching a child to see, but a child with potentially superhuman capabilities. Just as a human child learns to recognize faces, read expressions, and navigate spaces, computer vision systems learn to extract meaningful information from digital images, videos, and other visual inputs. However, unlike human vision, which is limited by biological constraints, artificial vision systems possess remarkable advantages. They can see across spectrums invisible to human eyes, including infrared and ultraviolet light, process thousands of images simultaneously without fatigue, maintain perfect attention for indefinite periods, and analyze visual data with mathematical precision that exceeds human capability. Modern computer vision has evolved beyond simple pattern matching into genuine visual understanding. These systems don't just identify objects in images, they understand spatial relationships, predict how scenes might change over time, and even generate entirely new visual content that's virtually indistinguishable from reality. This evolution has been driven by the convergence of massive datasets, powerful computational hardware, and breakthrough neural network architectures. The medical breakthrough we're highlighting comes from Kundu and colleagues with their paper titled LifWavNet, Lifting Wavelet-Based Network for Non-Contact ECG Reconstruction from Radar. This work represents a remarkable convergence of signal processing, machine learning, and healthcare technology that could fundamentally change how we monitor heart health. Traditional heart monitoring requires physical contact with patients through electrodes attached to the skin, creating discomfort and limiting mobility. The researchers asked a deceptively simple question: what if we could monitor someone's heart rhythm from across the room using radar waves? The challenge is enormous. Radar signals and heart electrical activity exist in completely different physical domains. The breakthrough came through a novel neural network architecture called LifWavNet, built around learnable lifting wavelets. Unlike traditional signal processing that uses fixed mathematical transforms, these adaptive wavelets learn during training to find the optimal way to decompose and analyze radar signals for heart rhythm reconstruction. The system achieved substantial improvements in both heart rhythm reconstruction quality and vital sign estimation, with direct implications for clinical utility in emergency rooms, home healthcare, and continuous patient monitoring. The efficiency revolution in generative artificial intelligence represents another major breakthrough from our collection. Researchers have solved a fundamental challenge: how to maintain the quality and diversity of sophisticated generative models while making them significantly faster and more practical for real-world deployment. Think of it like discovering how to paint a masterpiece in minutes instead of hours without losing any artistic quality. The solution involves breaking down the generation process into phases and using mixture of experts architectures that activate different parts of the network for different aspects of the generation task. This approach allows systems to allocate computational resources more efficiently, focusing processing power where it's needed most, while avoiding unnecessary computation. The implications are transformative. Hollywood-quality visual effects could run on smartphones, enabling democratized content creation. Complex generative models that previously required powerful server farms could operate on edge devices, bringing sophisticated AI capabilities directly to users. This breakthrough addresses the persistent challenge of making powerful AI systems practical for widespread deployment, bridging the gap between laboratory demonstrations and real-world applications. Security and robustness represent critical challenges as computer vision systems are deployed in security-critical applications. The research reveals breakthrough approaches for building digital fortresses that can withstand both accidental failures and sophisticated deliberate attacks. One key advancement combines adversarial training with carefully designed contrastive learning to achieve substantial improvements in model robustness without sacrificing accuracy on normal inputs. This addresses the long-standing trade-off between security and performance that has plagued AI security research. Another significant finding tackles the challenge of detecting synthetic images and identifying their creators. Researchers discovered that the internal workings of AI image generators naturally encode unique signatures, like digital fingerprints, that can be used to both detect fake images and trace them back to their source. These signatures persist even when images are compressed, cropped, or otherwise modified, providing new weapons in the fight against misinformation and deepfakes. The combination of robust training methods and detection capabilities creates comprehensive defense systems against visual deception. 5 key breakthroughs stand out as particularly significant for advancing both theoretical understanding and practical applications. First, the adaptive wavelets revolution demonstrates that learnable signal processing components can dramatically improve non-contact physiological monitoring, opening possibilities for continuous, unobtrusive health monitoring in previously impossible situations. Second, phase distillation methods show how to maintain generative model quality while achieving dramatic speed improvements, making sophisticated AI generation practical for everyday applications. Third, the solution to the security performance trade-off through combined adversarial and contrastive training enables robust systems without sacrificing accuracy. Fourth, the discovery that AI generators leave detectable fingerprints provides new capabilities for fighting synthetic media and misinformation. Fifth, advances in self-supervised spatial reasoning show how simple learning tasks derived from ordinary images can significantly improve AI systems' ability to understand three-dimensional relationships. Each breakthrough addresses fundamental challenges that have limited the practical deployment of computer vision systems, creating new possibilities for real-world applications. The LifWavNet paper by Kundu and colleagues deserves deeper examination as it exemplifies the convergence of multiple advanced techniques to solve a genuinely important problem. The challenge they tackled is like trying to reconstruct a symphony by analyzing the vibrations in a concert hall's walls. The information is there, but extracting it requires incredible sophistication. Their solution employs learnable lifting wavelets that adapt during training to find optimal decomposition strategies for radar signals. The architecture includes both lifting and inverse lifting units that work together to break down radar signals into multiple resolution levels, process each level appropriately, and synthesize the final heart rhythm output. One of the most innovative aspects is the multi-resolution short-time Fourier transform loss function, which ensures that reconstructed signals maintain both temporal accuracy and spectral fidelity. They not only look correct in time, but contain the frequency information doctors need for accurate diagnosis. The personal motivation behind this work is particularly touching. Dr. Kundu was inspired by experiences with elderly family members who struggled with traditional monitoring equipment, driving technical innovation through genuine desire to improve patient care. The technical innovation in LifWavNet demonstrates sophisticated multi-resolution analysis that bridges the gap between radar signals and cardiac information. Think of the system as having multiple microscopes with different magnifications, each optimized to see different aspects of the same phenomenon. The learnable lifting wavelets represent a fundamental advance over traditional fixed transforms, adapting their analysis strategy based on the specific characteristics of radar to cardiac signal translation. The lifting and inverse lifting units work in concert, decomposing incoming radar signals into multiple frequency and temporal scales, processing each scale with specialized neural network components, and then reconstructing the cardiac information through inverse operations. The multi-resolution short-time Fourier transform loss function ensures that both the timing and frequency characteristics of heart rhythms are preserved, crucial for medical meaningfulness. The system's interpretability allows researchers to visualize how different network components learn to recognize specific cardiac features, building trust essential for medical applications. This combination of adaptive signal processing, multi-scale analysis, and interpretable learning creates a robust foundation for non-contact physiological monitoring. The real-world impact of these advances extends far beyond laboratory demonstrations into transformative applications that could revolutionize patient care. Emergency rooms could begin heart monitoring the moment patients enter, without any setup time or trained technician intervention. Home healthcare scenarios could provide continuous cardiac monitoring without uncomfortable equipment, enabling better management of chronic conditions while maintaining patient quality of life. Newborn monitoring could occur without delicate skin contact, reducing infection risks and improving comfort for vulnerable patients. Disaster scenarios where traditional medical equipment is unavailable or impractical could still provide essential cardiac assessment capabilities. The technology particularly benefits elderly patients who struggle with traditional monitoring equipment, addressing mobility restrictions and discomfort that often limit continuous assessment. Beyond immediate medical applications, the non-contact monitoring approach could enable cardiac screening in public health settings, workplace wellness programs, and remote healthcare delivery where traditional medical infrastructure is limited. The combination of technical sophistication and genuine human need creates compelling use cases across multiple healthcare domains. Looking toward the future, computer vision is evolving from specialized tools towards Swiss Army knife systems that can handle multiple related tasks with high competence. The convergence of multiple technological trends creates unprecedented opportunities. Advances in hardware make powerful computation available in smaller, more efficient packages. Algorithmic improvements enable learning from less data with better generalization. The explosion of multimodal data enables richer, more contextual understanding. We're approaching AI assistants that understand environments and needs, just by looking around spaces, medical systems that diagnose conditions through subtle visual cues human doctors might miss, and educational systems that adapt teaching methods by observing student engagement through visual feedback. The integration with robotics promises systems that navigate and manipulate the physical world with unprecedented capability, understanding environments, adapting to unexpected situations, and learning from experience. These developments point toward truly helpful robotic partners rather than rigid automation, with vision and action capabilities that could transform how we interact with information and our environment. Today's journey through cutting-edge computer vision research reveals a field undergoing revolutionary transformation. The The 16 papers demonstrate sophisticated, principled approaches to increasingly complex, real-world challenges, from radar-based heart monitoring that could change healthcare delivery, to efficient generative models that could democratize content creation, to robust security systems protecting against sophisticated visual deceptions. These advances represent fundamental shifts in what's possible. The learnable wavelets that adapt to specific signal reconstruction tasks, the phased distillation methods making powerful generative models practical, and the multimodal fusion techniques combining different information types effectively. These innovations build the foundation for AI systems that truly understand our visual world. The human stories behind these technical achievements remind us that the best research stems from genuine desire to solve important problems and improve lives. These technologies have potential for meaningful positive impact across healthcare, security, scientific understanding, and numerous other domains where visual intelligence can make a difference. This research summary was created through AI synthesis using Claude Sonnet 4 2025-05-14 with text-to-speech synthesis powered by DeepGram technology and image generation through OpenAI systems. The content underwent human expert review to ensure accuracy and clarity, though potential oversights may exist in this synthesized presentation. All referenced papers from the archive preprint server provide detailed technical information for readers seeking deeper understanding. The synthesis process aims to make complex research accessible while preserving technical accuracy and highlighting the most significant contributions from each paper. This approach enables rapid dissemination of cutting-edge research findings to broader audiences interested in artificial intelligence developments. Join the AI Frontiers community by subscribing to our channel for daily insights into breakthrough research across computer science and artificial intelligence. Share your thoughts about these developments using hashtag AI Frontiers and explore the referenced papers for deeper technical learning. The future of computer vision is being written right now, and understanding these advances helps prepare for the remarkable changes ahead. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprintserver.org.